Hi everyone, welcome to CS 188 Section 4, and today we'll be talking about games, finishing up adversarial search, and then doing an introduction to MDPs, Markov decision processes. Okay, so for adversarial search, most of the time we've been considering an agent that's maximizing, like Pac-Man. They take an action, and then it becomes the minimizer's turn, who may be the ghost, and then we keep going back and forth until we reach some terminal state. So we either finish the game or we decide we don't want to search anymore and we call our evaluation function. But now what we want to consider is, what if the other agent that we're playing against is not a minimizer? What if there's something else? So if we draw the tree, so we'll still be maximizing. Pac-Man still wants to get the highest score. But the other agent will be this circle node, which we'll call the chance player. And we go back and forth and we do the same thing. We either reach the end of the game and get a score, or we have an evaluation function so we don't have to search all the way to the end of the game. So what is this chance node? What's this chance agent? Well, the chance agent could be pretty much anything. For example, they could be cooperative. They could actually be trying to help the maximizing agent. Maybe they're actually purely random. They just flip a coin to decide what action to take. And they could be many other things. So when we wanted to solve for having a max player and a min player, we ran Minimax, and that's how we decided what actions are the best to take. But now that we have a different agent that we're playing against, one that's not purely trying to hurt the maximizing agent, that we should think that there should be some other way to play and get the best score. So this brings us to Expectimax search. So in Expectimax, what we do is we assume the other agent has probabilities over actions. So what do I mean by this? So let's go up to this Expectimax tree, and let's say I'm a chance node, and I have these two actions to consider. So let's say for this agent, I have a 0.6 chance of going left, and maybe then a 0.4 chance of going right. Or if I'm at the chance node at this state over here, then maybe I have a 0.1 chance of going left and a 0.9 chance of going right. Okay, so now that we've defined our chance agent, how do we calculate the actual value? So the chance value is going to be the weighted sum of the children times the probabilities. So it's going to be the sum over all actions of the probability of taking that action times the value of the state that it goes to. So let's fill in, let's do an example. So let's say this is 100 and this is 10 for the terminal value. So what would the chance value be? So it'd be 0.1 times 100 plus 0.9 times 10, and that equals 19. Okay, so now we know how to run Expectimax search, because we know how to calculate the values at the chance nodes, and we already know what to do for max. So when is this good, and why would we ever want to use Expectimax search over Minimax search? So I'm going to create a game with a max player and a min player. And it ends at some terminal values. Then I'm going to do the exact same structure, but instead have a chance node. And even further, I'm going to make sure they have the same exact terminal values. So 100, 0, 20, 40, and 100, 0, 20, 40. And I'm going to define my chance agent as being uniform at random. So they have a 0.5 chance of going left or right, no matter what. So that's my max, that's my min, this is my max, this is my chance. So let's fill in the values for these trees, and then we'll take a look at them. So I'll do this pretty quickly. So for max min, we start at max, we go to the left. We're at min, 100 or 0, we choose the min 0. We go to the other min, 20 or 40, we choose the min 20, and max chooses the larger one, 20. Now for Expectimax, we start the max, we go to the left node, the chance node, and we do 0.5 times 100 plus 0.5 times 0, and that gives us a 50. We go to the other side, and for the chance node, 0.5 times 20 plus 0.5 times 40, that's 30. We take the max, and that's 50. So let's take a look at this. So the Minimax tree search said, hey, go right at the top, while the max chance one said, hey, go left. So as you can see, the Minimax is pessimistic. It assumes that, okay, I should play it safe, and although I could get 100 if I go left, I could also get 0. So I'm going to go to the right, where it's either 20 or 40. While the Expectimax search with the chance random player says, okay, well, I'm going to assume that the other player just, tosses a coin, so then the left side actually does look pretty good. Even though there is a 0, the 100 is pretty high. So as you can see, the model of our agent and how they choose their actions affects a lot how our player acts. Okay, so now we're going to move on and we're going to talk about utilities. Okay, so what are utilities? Well, utilities, they describe an agent's preferences. So for example, they might describe whether I prefer chocolate ice cream or vanilla ice cream. But in general, we could maybe think that they're prizes, and we'd maybe label them A, which could be my chocolate ice cream, or maybe they're B, vanilla ice cream, etc., etc. So we care about these utilities because we have these agents and we want to maximize their utility. So Pac-Man wants to maximize his utility. Now, what is Pac-Man's utility? It's, that's up to us to decide. In Project 1, it was eat as many pellets as possible. In Project 2, it's get the maximum score, which means eating pellets and eating ghosts after you frighten them, but not getting eaten by ghosts. So it really depends on the agent in the game. But what we want to do is we want to compare utilities to each other, because an agent has choices about how can they maximize their utility. So we need to introduce some notation to be able to compare these. So the first one is simple preference. So if an agent prefers A to B, we write it as A to B. So what does this mean? This means that the agent for the utility of A is greater than the utility of B. So the agent prefers prize A over prize B. Then we also have indifference. So we say that A is indifferent to B, and that's tilde. So what does this mean? This means that the utility of A is equal to the utility of B. Okay, so now we can define a whole bunch of relationships, and we care about rational preferences. So what are rational preferences? Well, they follow certain axioms. So for example, here's an axiom. So we say if we prefer A to B, and we prefer B to C, then this implies we prefer A over C. So this one's called the axiom of transitivity. And if you look on the sides, there's a bunch of other axioms. And what they help us do is they help us to compare utilities to each other. And you can view these, they're very similar to just Boolean logic. So if you look at them on the slides, if you think of the utilities A, B, and C as numbers, then it should make hopefully some intuitive sense based on what you've learned before. We also define a lottery. So for lottery L, for example, if we are considering two prizes, so if we have a probability P of getting A, and we have a probability of getting 1 minus p for getting b. Then the utility of that lottery is the probability of A times the utility of A plus the probability of B times the utility of B. Now, why might we care about this? Well, an agent might have a utility, but it's composed of a bunch of other utilities. So, for example, maybe my utility is L, and for A is, my utility of eating that ice cream, and utility B is of going and exercising. So now my utility is more complicated. It's a weighted sum of other utilities. Okay, so now we're going to talk about MDPs, which are Markov decision processes. And we're just going to do an introduction today. So for a Markov decision process, we generally consider an environment. So the usual one we consider is this grid world. And let's say our agent is in there. That's maybe their Pac-Man. And in some states, the agent might get a lot of good rewards, like plus 100, but maybe in some other states are really bad and they'll get minus 1,000, and maybe there's some states that they can't even go to. So let's say this is our world and our agent lives in this world. So the goal of MDPs of the agent is to maximize the sum of rewards. So this is the same as a bunch of other problems that we've encountered. We want to do as best as we can. So first, we're going to talk about the framework for MDPs. So this is very important. This is how all MDPs are framed. So in an MDP, we have states. Little s is what our current state can be, and it comes from the whole set of all possible states, big S. So big S would be all positions on this grid, and little s would be the current state of Pac-Man. So a lot of this will have repeats from search. Then we also have actions. So little a and big A. So in this grid world, Pac-Man can go left, right, up, or down, and little a is the current action that Pac-Man takes. Now here's something new. So we have a transition function. And this is denoted as big T of the current state S, the current action A, and the next state S prime. So you can actually view this as a conditional probability. So this is the same as what is the probability of the state S prime given that you were in state A and you took action A. So let's consider an example. So let's say we have this little Tetris looking world, and Pac-Man's right there, and Pac-Man can go left with, let's say, 0.1, can go up with 0.3, can go left with 0.6, and we'll call these states A, B, C, and D. So for example, the probability of going to state B, given you were in state A and you took action right, equals 0.1. So that's what this transition function is. We also have a reward function. And this is represented similarly, where we have a reward R for our current state S, our action A, and the next state S prime. So if we look at this grid world up here, if Pac-Man was near this top right part right here, and Pac-Man moved into it, then the reward Pac-Man would receive would be plus 100. So now we can define our goal a little more concretely. So our goal is to learn a policy, the best policy possible, pi star, that maps state to actions. Okay, so let's break this down. So in general, we denote policies as pi. That's a common way to denote them. And we put the star there saying that we want the best policy possible, the optimal policy. And what does the policy do? It says if you give the policy a state, it'll output what action you should take. So let's do an example. So let's say Pac-Man was up here in green. So that's the state right here. That's the grid cell. Then the optimal policy, if you compute it, which we'll talk about not in this section, but later, I'll give it the state, and it would give me the optimal action, which would be to go and get my plus 100. So that's what pi star tells you. Okay, so now we should actually talk about rewards and what the goal of pi star is. So for rewards, what makes the most sense is to talk about the total reward. So the total reward is the sum over all time, so from 0 to infinity. So we assume the agent is always playing, and at every time step the agent gets a reward. However, we actually might prefer rewards that are sooner, because reward at time 0 might be more important than a reward at time 1000. So then what we can do is we can introduce something called a discount factor, which I denote as gamma. So what this reads is that the later in time we go, actually I should also mention that gamma is between 0 and 1. So we can see that as we go farther in time, gamma gets exponentiated larger, and because it's between 0 and 1, it'll become very, very small. So if we draw a plot of t versus gamma, it'll look something like this. It'll get small very fast. And this is called the discount factor. Now, let's do an example to show why it's a discount. So let's say we have this simple environment, and it's just kind of like a 1D grid world, and the agent is done here, and the agent starts here and goes to the right. And at each time, it's getting 1 reward. Now let's say gamma is 1. Then the total reward is going to just be the sum of all the rewards, so that'll be 3. But now let's say gamma equals 0.1. So the total reward is going to be, let's apply this equation. It's going to be gamma to the 0 times 1 plus gamma to the 1 times 1 plus gamma to the 2 times 1. Sorry, should be 1. So if we rewrite this, it would be 0.1 to the 0 plus 0.1 to the 1 plus 0.1 to the 2. So as you can see, is we care more about what happens before compared to what happens later. So that can give our agent some better behavior, but also another reason is that it helps our algorithms converge when we're trying to learn this policy pi star, which we won't talk about now, but you will have covered in lecture, and we'll be talking about in the subsequent discussion next week.